Uh, Good morning, everybody. My name is Tim Gettner. I'm a professor here at UCSD in the psychology department. I was trying to think about the best way to introduce the next speaker. Someone once told me that if you're going to have a philosopher speak, only have one philosopher speak. When it came time to organize this symposium, I really couldn't think of anyone that was more appropriate for that select role. Like many of you who have followed this tradition of the generative mind and have looked back across history, you'll know that it runs through a number of very deep intellectual discourses, one of which is the classic work by J.J. Gibson. And like you, I read Gibson when I was in early graduate school, probably, and like many of you, didn't really understand it. But appreciated that there was something very deep inside what he was doing. And it wasn't until many years later that I read a book by our next speaker that really clarified that issue and laid out the depth of the argument that Gibson was making about the structure of what we know and what we can know about the outside world and how that comes to bear on questions of the nature of knowledge and representation more generally. So it's my great pleasure to introduce to you Mark Bickard. He's the Henry Luce Professor of, let me get this right, Cognitive Robotics and the Philosophy of Knowledge at Lehigh University. And he's going to talk to us today about a straightforward idea of how does or how can a brain represent.
Well, good morning, everyone, and thanks to the organizers for the invitation. I'm going to talk about basically three things. I'm going to start out with a philosophical realm of problems that arguably does not have a solution in the literature. Then I want to suggest an alternative model that I want to argue does offer a solution. And then I want to argue that this alternative model actually does make some very strong connections with and interfaces with what we know about how the brain actually functions. So, standard models of representation, virtually all are some version or another of correspondence. We can have causal correspondences between something that presumably represents in the brain and something being represented in the world. We can have nomological, lawful correspondences, structural correspondences, informational correspondences. That's the most dominant in most of this literature. The symbol systems, neural nets, and so on. These go all the way back to the Greeks. The signet ring into wax is a correspondence model. The Greeks thought of thinking about something as akin to pointing to it, or talking about something as akin to pointing to it. Another version or perspective on these correspondence intuitions. It's got some problems, and every one of these particular ones of Fodor and so on, have particular problems, but there are two general problems I want to mention that seem to afflict every one of these. One is, if the correspondence exists, say a nomological correspondence, then the representation exists, and it is correct. But if the correspondence doesn't exist, then there's no representation. No representation to be incorrect. So a fundamental question is, how can a correspondence exist with something that doesn't exist? Or how can a correspondence exist with a falsity, whatever that might be? I actually want to strengthen the question. The question of how can a correspondence exist and be false was approached by a lot of folks in the 80s and 90s. The issue seems to have faded a bit because nobody came up with a solution. But it was all done from the perspective of some observer. How could Fodor be wrong about something if somebody else was looking at what was going on in Fodor's head and analyzing its relationships with things going on in the world? A stronger version, however, is how can an organism detect the truth or falsity of its own representations? A classic argument is that the organism can't do that because it would have to step outside of itself to check if the representation and the represented fit each other. You can't step outside of yourself, so you can't check. This is a classical radical skeptical argument, and it's been around for a while, undefeated. It's often been ignored because nobody seems to have solved it. So we really can't do anything with it, so let's just forget about it. Most skeptical arguments, there's actually a huge family of skeptical arguments, conclude with some version of fallibilism. We can be wrong. These are not, in my judgment, intrinsically problematic because fallibilism seems to be correct. But the radical skeptical argument, the one I just outlined, is much more problematic. The radical skeptical argument seems to make assumptions of an other end of our representational correspondences superfluous. If we can't ever check, what's the point of even positing that any such other end exists? This can yield idealisms, and maybe there is no other end. We just live in this world of our representations and so on. However, if the radical skeptical argument conclusion were correct, error-guided behavior and learning would not be possible. If we can't ever check to see if we're in error, the corrections involved, the adjustments involved in error-guided behavior and learning would not be possible. But we know these occur, so there's got to be something wrong. There's got to be an error somewhere in the model or in the argument itself. And I argue that the radical skeptical argument is actually a reductio of these correspondence models. Since the notion of information is the dominant one, I wanted to say a little bit more about it. The standard interpretation or understanding of information is as correlation. And correlation, in fact, does support representation in a certain sense. It supports representation if A and B are correlated and you know about B, you can make inferences about A, so B can represent A. But you've got to know about all these things, or some brain does. So it presupposes representation to be able to do this kind of a thing. On the other hand, correlation is needed for any kind of control, any kind of contact with the world, any kind of sensitivity to the world. You've got to have some sort of correlated signals that provide that sensitivity. So control information is necessary, but it's neither true nor false. So it doesn't solve either of those two problems I mentioned before. So the issue of how anything can ever be correct or incorrect, true or false, and so on, the basic normativity issue about representation still exists, and we still have the problem of how it could actually be realized. So here I start with at least a few ideas about an alternative. This is a pragmatist orientation. Pragmatism in the sense of purse. Any complex agent must have some sort of functional indications of what interactions are possible. So a classic in the sense of a few decades, realm in which this was explored, frogs see flies and maybe flick their tongue to eat the flies. What is it that the frog is representing? Turns out if you flip BBs or pebbles, the frogs may flick their tongue at the BBs or pebbles. So is the frog representing flies and somehow incorrectly representing pebbles? But what makes that incorrect? Or is the frog somehow representing a class that includes both flies and pebbles and so on? A lot of exploration of that. But these indications, noticed, if I'm a frog, I could flick my tongue this way and eat a fly. I could flick my tongue this way and eat a worm. whatever. Those indications, interestingly, can be true or false. The correspondences to fly, that's contact, that's correlational information, but it either is there or not. There's no way for it to be there and be false except with respect to what I anticipate as a frog that I could do. So it's the indications into the future that can be true or false here. This constitutes the emergence of a truth-value normativity, and as realized in a special kind of functional normativity, namely the functional normativity of indicating what I could do next. This doesn't look like standard models of representation. I can fill it out for a number of things. Here's one challenge. What about small objects? Notice that these indications of future potentialities can branch. The frog can have, I could flick here and eat, I could flick here and eat, I could flick here and eat. They can also iterate. If the frog, move to the left, maybe some other things come into range. These branchings and iteratings can generate webs, and in complex organisms can generate extremely complicated webs, and there are invariant patterns in these webs sometimes. So if you consider a small toy block for a toddler, the toy block affords, I'm using a Gibsonian word deliberately there, many different kinds of manipulations, many different kinds of visual scans, and they are related to each other in the sense that you can move within that structure, that organization. And furthermore, that organization is invariant with respect to lots of things. It's invariant with respect to dropping the toy block on the floor, putting it in the toy box. It's not invariant with respect to crushing it or burning it. This is basically a Jean Piaget model. And it's possible to do this, to borrow from Piaget, because he's one of the few people who does actually have an action-based, a process-based, a pragmatist-based model. Another challenge, I don't think I'm going to go into detail here, but just to mention it. Okay, maybe you can represent blocks and other physical things like that, but what about abstractions like the number 3? So that's another challenge that has to be met. Notice, the basic problem of truth and falsity that I mentioned with respect to correspondence models is resolved here. There's no difficulty in an indication that something is a possible interaction existing, but being false. And furthermore, organism detectable error is, at least in principle and quite often in practice, attainable. If you engage in an indicated interaction and the interaction fails, it goes off the rails, the indication is or was false and falsified for the organism because that failure is functionally internal to the organism. Okay, how is this realized? How does it actually happen, or might it actually happen? I've talked about indications and anticipations of possibility being of potential interactions. Notice potential here. A, it's in the future, and B, it's modal. Successful interaction requires coordinative timing. So if I'm actually going to interact with the world in some way, if I'm actually going to engage in one of these indicated possibilities, I need to have coordinative timing with the world that I'm interacting with. Turing machine mathematics does not give me timing, it gives me only sequence. So it gives me a step in the direction. It's a process formalism, but with Turing machine mathematics, and only Turing machine mathematics, you could never build a system that walks. Computers do have timing. They're, in that sense, a bit more powerful than a Turing machine formalism will capture, but they have timing with a timing circuit driven by some sort of master clock or clocks. There's a simpler way to do it, and that is to make everything a clock. So with everything a clock, clocks are just oscillators, and oscillators can modulate each other. So we have a different way of thinking about the functional relationships here. We've got clocks, i.e. oscillators, everywhere, and they modulate each other's activity. This gives us free timing everywhere. We don't need separate timing circuits, although we might have them for other conveniences. We have Turing machine plus power, because you can get a Turing machine out of this kind of a model, but you also have timing. You can get the Turing machine because the limit case of A modulating B is A switching B on and off, and you can construct Turing machines out of switches. So this is at least, at first glance, a viable way of thinking about functional architecture. And in fact, evolution has created a toolbox of many, many different kinds of oscillatory and modulatory resources. They involve both neurons and glia, and this is where the interface occurs. Probably much of what I'm about to say will be familiar with, or to many of you, but let me just point it out. At the neural level, we have silent neurons, never fire. Don't make a whole lot of sense if threshold switch processing is the fundamental functional nature of things. We have non-zero baseline firing. Threshold switches don't have non-zero baseline firing. Those can be accommodated in various ways, but they're at least anomalous. We have gap junctions, volume transmitters that diffuse throughout local volumes of intercellular fluid, resonance frequencies. Some of you folks here in California have talked about that. I don't know of any direct evidence that resonance frequencies are functional, but my own guess is that they're so easily accessible, it would be very surprising if evolution didn't figure out some way to make use of it. And we can go on. If we check with astrocytes, astrocytes have transmitter receptors, transmitter substances in the intercellular fluid. They themselves secrete transmitters, again, as volume transmitters. They have gap junctions with each other that support calcium waves moving through populations of astrocytes. They can modulate the degree to which a given synapse is a classical versus a volume transmission by surrounding it. If it's completely surrounded, then no volume diffusion occurs. If it's only partially surrounded, then you'll get both classical synaptic transmission as well as volume transmission. They will modulate synaptogenesis. They form little local bubbles in which they influence the local environment modulation. I like a quote from Nadergaard here: astrocytes tell neurons what to do. They don't just clean up the mess. For an evolutionary framework within which to think about this, transmitters evolved from colony regulating hormones, which would obviously be volume transmitters in a certain sense. They became volume transmitters. Gap junctions are also very early. Synapses are actually, from an evolutionary perspective, late. So you have an evolution of more and more specific and smaller local, more and more local kinds of influences. Notice that the transmitters are still local, in that sense, local hormones. So we still have the volume hormones, the volume transmitters, but we also now have these very local ones. Most of this is highly anomalous if the functionally relevant processes are threshold switches or nonlinear nodes or something like that. Why did evolution bother to create all this? Well, it makes sense for evolution to have created all this if, in fact, what these constitute is a rich toolbox for engaging in various kinds of oscillatory and modulatory functional processes. We have always ongoing oscillatory activity. There's no passive processing here. Even for silent neurons can carry slow wave potential waves and thereby modulate and influence things that are going on near them. There's modulations of many forms and multiple scales. We have larger and slower scales. Astrocytes can modulate what's going on in these bubbles that contain many, many neurons. We also have smaller and faster scales, the gap junctions being the smallest and the fastest. One point I would like to make about this is to point out that the slower scale processes effectively set parameters for the faster processes. So the slower scale processes, if you've got something happening very rapidly and then you have something moving very slowly, the slower process is effectively constant for at least some relevant parts of the very fast processes. By setting these parameters, they induce and modify the spaces of the dynamic trajectories for the faster processes. This is the dynamic system equivalent of programming. So the larger and slower processes, in effect, program the smaller and faster processes. In doing so, in setting the parameters for fast processes, slow processes are setting them up for forms of further interaction, of further dynamics. This is a setup or preparation form of anticipation of what further processes are going to occur. These setup anticipations can be correct or incorrect. It may be that how the actual flow occurs goes outside the realm of what is being set up for and requires some sort of a recalibration. Notice that makes them true or false as indications. It indicates it's via setup that whatever is going to happen next is going to happen within this realm, and if it deviates from that realm, then it has been falsified. A term that I have adopted for this is microgenesis. It's fairly close to how the word microgenesis is used in the literature, but it also has a few differences. But anyway, it's a handy word for it. I might note that if this failure of setup anticipation, this failure of microgenetic anticipation occurs, and that occurrence destabilizes the setup process itself, then we have a primitive variation in selection learning process. It's a local evolutionary epistemology, and that's an entree into talking about other kinds of psychological mental phenomena. Okay, the suggestion then is that the brain represents, with truth values, via functional anticipations of local levels of interactions. This, so I argue, is the basic form of representation, out of which more sophisticated kinds of representations are evolved and constructed. I gave the example of small objects, of how you could construct a model of representing small objects out of this model of indicated anticipations. Note that not all species are capable of some of these more complex forms of representing. I doubt that frogs are capable of representing permanent objects, but they certainly are arguably capable of representing it in some sense. So this movement from representation to learning, as I mentioned, is an entree into further process models for other kinds of mental phenomena. I would also point out that anticipation in this model is itself normative, and that the emergence of that normativity I haven't addressed in this talk. I can say more about it if you would like. The conclusion then is that the brain represents via future-oriented preparatory anticipations. It's not just kinds of input processing, although certainly input processing is essential. This makes sense of what are otherwise rather anomalous processes in the brain, anomalous in processes for both neurons and astrocytes, and it accounts for representational truth value. And neither of these neural nor astrocyte processes nor representational truth value have really been accounted for within correspondence models. So that's the basic conclusion. I have a few other things I would like to mention, especially given that great talk that we just heard. It might clarify a few things if I mention I was also strongly influenced by McKay, by analysis by synthesis. But I decided that McKay had one part of it wrong, and that is he was talking about synthesizing and in that sense predicting the input stream. I was worried at the time about representing, and I was very suspicious about all kinds of issues about alphabets in Turing machine theory. So the tape with all of its symbols on it were often taken to be, tapes were often taken to be either the environment or else representations of the environment. And that was the problem I was trying to solve. So in some sort of inadvertent way, begging the question was an issue that I was concerned about. So along comes McKay, and I think he had things right about the receiving part of what's going on and the anticipating part of what's going on are not the same process, although they're obviously strongly related. But it seemed to me that the recognition of a particular input alphabet item was itself an epistemic problem. And I wanted to make sure that I wasn't assuming this kind of an epistemic problem as being unproblematic. It was precisely what I was trying to take as problematic. It seemed to me that what the system could actually anticipate was not the inputs per se, but rather the processes that were evoked by the inputs. So that led to this model of the setup anticipation, that you're anticipating the internal processes. In some cases, this is going to be extensionally pretty equivalent to anticipating the inputs, but in other cases, they will be quite different, and in my judgment, importantly different. Okay, that's where I'll stop.
Okay, we have time for questions. Terry?
So I'd like to give an example I think fits into your framework, and it goes back to your comment at the beginning, which is how can you learn something if there's no error feedback, right? Mm-hmm, mm-hmm. So we have a system in the basal ganglia which learns through experience with something called reward prediction error. That is to say, if you do something, take an action, and you're expecting a particular reward, if you get more reward than you expected, you change, using dopamine, you change the strengths of the weights now so that you can expect more reward for the same input. Or if you get less, you decrease those weights. So using the simple algorithm, it's actually, this is temporal difference learning that comes from reinforcement learning. It's possible to train a very complex, a very simple network, okay, to create a value function, a neural network, to create a value function that allows you to make predictions for new inputs that are coming in that you've never seen before. And this was the way that AlphaGo was able to train by playing itself millions of times to play Go at a very high championship level, and in fact was creative. So this idea of error feedback is an important one, and it's actually, it takes place in many other parts of the brain. In the cerebellum, predicting sensory feedback. You use the difference between what you expect and what you get in order to tune up the network. Now, here's the amazing thing, though. If you look at transformers, how are they trained? They're trained to predict the next word in a sentence, just the next word. They don't have to predict meaning or anything, but they have to create, in order to be able to make that prediction, they have to create an internal representation of meaning. Otherwise, they're not going to be able to answer questions. So it's amazing how far you can get with very simple learning systems, just predicting what happens next.
Okay, and the question is,
Okay, the question is, how do you go from that to the more abstract level? And I think you've actually alluded to that.
my response, I think, tell me if I'm addressing it correctly, is that, yeah, you have to train. So it's the training that constitutes the definition or the imposition of some normative issue. And so what makes it normative is the person or the system or the designer for the training itself. If this were to occur without the normativity coming from me, the user, or something like that, it would be, I think, better modeled as a kind of a settling process, like a soap film settling into a shape within a wire rim. It's much more complicated than that, but it's very useful to have things that settle into a particular condition. And I consider a lot of the phenomena you're talking about, like AlphaGo, as extremely complicated, extremely impressive settling processes. But the normativity that's involved is the normativity of the Go players and the designers of the program. So what I'm trying to do is to account for that normativity.
Okay, thank you.
Hi, thanks for the talk. I was curious about this last comment you made about the prediction not being only of input. When you said that, the only thing that came to my mind maybe is like anticipation of like future actions, but I would like you to just comment a little bit on like what, if not the predictions of input processing, what else do you have in mind when you say that?
Well, it's anticipation of the future flow of process within these neural astrocyte systems. So they are going to be participating in interactions. So in effect, it's anticipating the local involvement in some sort of interactions with the world.
So just anticipation of the cognition in general, the cognition dynamics?
No, arguably this is down at the level of the actual ionic flows, transmitter flows, diffusion processes, and so on.
And what role does that have? Like in terms of the
Well, it's those
functional
processes at the smaller, faster scale that are going to be engaged in interactions with the world, and it's those processes that therefore will encounter conditions in which they satisfy the anticipations and conditions in which they don't satisfy the anticipations, and therefore those anticipations end up being true or false, depending on whether that satisfaction occurs. Notice the problem with the radical skeptical argument. There's many different ways of looking at it, but one way is you can't detect error unless you can compare the representation with the represented. And with a correspondence model, there's no way to do that without stepping outside of yourself. But in this model, the comparison is something internal. It's the internal actual flow of process with the internal anticipated setup flow of process. And so you've got access to both of them, and the comparison, in a certain sense, can be made right there.
Thank you.
Could I maybe ask one question that goes back to an earlier point that you made about the normativity? And if we imagine sort of neural systems and maybe more accurately organisms as these sort of nested kind of collections of interacting processes across scales, then in a sense it sort of has to be behavior or the sort of outward expression of those emergent processes that ultimately set some kind of normativity. And this maybe gets back to an earlier question about the scale at which those feedback processes or the predictions might be sort of realizable across the system. And is it your sense in which, in order to sort of get around the radical skepticism, you need to have the effects of behavior sort of kind of replay down across those scales, or is it somehow more transitive that once you get that normativity into the system somehow, that the internal processes don't even really need to directly reference that? Does that make sense?
I'm not sure. Let me try and answer. One place where this model is extensionally roughly equivalent, it's not processually equivalent, but it's extensionally equivalent with the standard analysis by synthesis framework, would be habituation.
Mm-hmm.
So if you habituate a cat to a single tone, a well-habituated cat never gets above the first cochlear nucleus. It's not a simple suppression, because if you lower the volume of the tone, the cat arouses. A classical way of interpreting that is you've got a subtraction process of some sort, where the anticipated input flow is subtracted from the actual input flow, and you want zero.
Right.
As I say, extensionally roughly equivalent to that would be an anticipation of what is going to be going on in the first cochlear nucleus, because that's whatever is going on there is what is evoked by those input streams. So you don't get a whole lot of important difference there. But now, let's consider a rat on a shock grid. So we've got a rat sitting on a shock grid, you get a tone, and a little bit after the tone you get a shock. There's a flow. This one crosses modalities. You can't habituate pain, according to this model, a different part that I haven't talked about. How can you successfully interact with that input flow? Well, you can successfully interact with that input flow by changing the input flow, by jumping up on the shelf and avoiding the shock. You can't do that very well with an anticipation of inputs per se. I'm not sure that answers.
I think it does, but I guess it's a question about the scale at which that behavior would ultimately be affecting. So if you're talking about anticipatory processes in the context of glia, right? Does the model require that behavioral level anticipation is actually kind of percolating down to those levels?
I haven't said anything in this talk about macro processes in the brain. I do have some publications about that. Roughly speaking, these kind of local processes self-organize with respect to each other in the whole brain. And so the brain is doing exactly what you're talking about, but it may or may not involve parts. So, the Sokolov inhibition, or habituation, doesn't get above a certain level. If you have a rising falling tone, you get a small spot in the temporal lobe. So it takes a bit more smarts to anticipate that. And the original response is going to be arousal. It's going to be the whole brain. But then as the brain discovers how to anticipate the flow, it may be the case that it only takes a much smaller part to do it. So the answer to your question is, it's going to depend. So like the tone habituation ends up not requiring very much. But avoiding the shock ends up requiring quite a lot, including muscular control and so on.
All right, we have time for maybe one more question.
Okay, thank you. So thank you so much for such, thought-provoking presentation. And, you generate a lot of processes in my brain, so I'll maybe, I'll maybe express some thoughts in anticipation that a question will emerge.
Okay.
So I think the basic premise of representation, right? To me, it seems that there is this sort of tendency to think that a label to some other stimuli is a representation. And I think, coming from text, we give labels to things. And I was wondering, assuming that maybe the notion of representation in some sense is wrong because it just corresponds correlations between processes, it made me think about, the question of metaphor. I mean, is any representation basically some kind of a mapping, especially if you think about metaphors not just in a language, but metaphor mapping between different modalities. So if you think about language and image, like, all these claps, the language and image pre-training, or especially in audio, language and audio pre-trainings, you can think about them as representations, but you can think about them as mappings. And then kind of the next thought that came to me was, once you refer to Piaget and the fact that, there is pragmatics. So we actually can understand metaphors through pragmatics. Otherwise, it doesn't really kind of resolve it. So I was kind of trying to formulate now a question, and that is, in that notion of the role of language and how it maps to meaning, and maybe in that sense, how language explains our visual modality or auditory modality, where the synchronization is actually even more required. My maybe central question or hypothesis would be, is it really possible for these mappings or representations actually to create things, as you said, that maybe cannot be proved or cannot be falsified, like totally creative mappings? So if you think about mapping, you write music to a picture, or write music for a film, right? These mappings exist in our brain. Once we establish that metaphorical mapping, maybe that sequence of, so this kind of a sequence of signifiers, right? This kind of in the linguistic notion, or maybe in Lacanian notion, you create a sequence of signifiers. Once you establish the metaphor, it's done. You understand it. How does that relate to, the brain dynamics, the brain processes? Is there some kind of a process that you generate mechanisms that anticipate? Once they correlate enough, you feel that the representation was established, and then that makes the meaning?
I think I distinguished at least half a dozen issues and questions in what you were saying.
That's what I thought. It's a flow, hoping to emerge from something.
Pick one.
Okay, here's an attempt at maybe a couple of them. First of all, our thoughts about representing have been classically dominated by what we take to be external representations, pictures and statues, and so on. And this goes back to the Greeks again. And notice the signet ring in the wax leaves an impression that is in fact structurally correspondent to the ring itself. Extremely appealing. That and its descendants were the dominant way of trying to think about representing for centuries, millennia, as a matter of fact. But it ends up not working. But part of the problem then is that these things we call representations in the world function differently than things that we call representations in the mind. Things that we call representations in the mind could be translatable, could be interpretable in the sense that representations in the world are, but into what? And so you end up having to have some sense of representation that's emergent in its own right, for which you can then define all kinds of other stand-ins. So the whole mapping notion, I think, is a very powerful notion, but it's mostly a powerful notion for things that we call representing in the world. If you try to do the mapping notion in the brain, mapping into what? Mapping into other representations? Well, maybe you can do that a step or two, but you can't do it indefinitely. And you never end up with an explanation of the emergent representing itself. So that's with respect to analogy and metaphor. One of the things that this kind of a model leads to, and this is right there in McKay, I think it's one of the major advances that McKay made with analysis by synthesis, is that you have an active mind, an active brain, that actually constructs things, and you can get overlaps of those construction processes. And overlaps of the construction processes can give you senses of associations. They can give you senses of analogous connections. They can give you senses of metaphorical connections. So via the fact that these things have to be constructed, they're not just simply sitting there to be interpreted with maps, but rather they have to be constructed, you can get a lot of these phenomena out of the relationships among the constructive processes. So there's maybe 2 of the 6.
Oh, great. Well, let's thank the speaker, and we have a short break.